Right, okay, we're carrying on with this paper. Question number 6. Student uses this method to investigate osmosis. Osmosis. What is osmosis? That's the question. Osmosis. Right. Link it to water. Is the movement or diffusion of water, movement of water particles or water molecules, right? First thing, from an area of, now I like to use the word high just because I've seen that a lot in the mark schemes, from an area of high water potential, from an area of high water potential to an area of low water potential. Normally people write from an area of high water, from an area of high water concentration to an area of low water concentration through a permeable membrane. And that's it. So whenever you've got water and it's diffusing, think of the word, and they like to see this word. Okay, so what we've got is we've got 3 potato bits here, and we're going to cut them into 5 centimeter long, dry the surfaces, measure the mass. So this is mass before putting them into the solutions. So this has got sugar solution, this has got distilled water, and this is in normal air. Put a bung on so there's no evaporation or anything. Measure the mass of each cylinder again, measure their lengths using a ruler. Okay, we want to see whether they've increased in mass and length. Okay, so this is what we're trying to test is diffusion. Once again, let me get rid of that. There you go. Right. There you go. Right, we've got that. It says, get it out of the way. Turn around the microphone. Right, okay, let's crack on. Okay. Yeah, there you go. There's osmosis. So what did we say osmosis was? Was the movement of water particles through a permeable membrane. Right, they've written the word partially. P-A-R-T-I-A-L-L-Y, partially. Right. State the independent variable. The one that you're gonna change, yeah? It'll be this content, it'll be the solutions or the contents, yeah? So in this case it's the sucrose, the distilled water and the air. That's the independent variable. Remember there's 3 types of variable. What are they? Independent is the one that you're in control of, you're going to change. Dependent variable is the one that you're going to measure, and control variable is the one you're going to make sure that is the same so it doesn't affect or influence the outcomes of the experiment or investigation. Osmosis is affected by surface area and volume of a cylinder. At the start of the experiment, each cylinder has a radius of 25 centimeters and a length of. Right, all they want you to do is substitute the values in, so it's a calculator thing. So what I would do is, can you see that there? You put 2 open, okay. They've actually told you that you're going to use 3.14. So 3.14 close bracket. So I've done the 2, I've done the pi. I'm going to do open bracket. The radius is 0.25 centimeters, 0.25. And then we need L is 5 centimeters. Then we're going to add that bit plus 2 open bracket 3.14. You can put times, it's not a problem. I've just got a habit of doing. The radius is 0.25 and then it's squared. Don't forget that. Put that into the calculator and you should get 8.2425, and we can round it off 8.2 or 8.24. Any one of those answers will do. Right, now we're asked to work out the effect of surface area. So the bigger the surface area, the larger the surface area, the larger the surface area. I'm just being lazy here. The larger the surface area, you do not do this in the exam. The larger the surface area, the larger surface area, the greater the rate of osmosis. So what we're saying is increasing the surface area increases the rate of osmosis. Because why? Because there is more contact between, if I can spell between, the potato surface and just say liquid or gas. Another variable, control variable. So we're looking at a control variable. The type of potato species or potato, because they might have a different structure. Temperature also affects it. Temperature. Okay, so now here is right. Okay, so we've now got the original mass was the same. The final mass in the concentrated solution has gone down. This has gone up and this has gone down. This has gone down more than this. So this is down more than this. This has gone down more. Yeah, oh no, we're not going to say more. So this has actually gone up. We're going to explain. Right, okay, so they're saying explain the changes. Right, okay. So this is how they want it. I've just looked at the mark scheme. Right. So with, oh my goodness me, with the concentrated sucrose, with the concentrated sucrose solution, the mass goes down, decreases the most because it because it has the greatest or the highest concentration gradient or water potential gradient, all right, between the solution, doubly solution, between the solution and the potato. Right. With, oh my goodness me, with the air, let's have a look. With the air, a small change occurs because, why does a small change occur? Because of evaporation and not osmosis. It's more, I think it's evaporation. I suppose it's still osmosis. Okay, so yeah, so it's evaporation, not osmosis. I've just checked that. Because osmosis would mean movement of liquid water. Right, number 3 is the distilled water. With distilled water, there is an increase in mass as the potato, as water moves into the potato, as it has a lower water potential than the solution outside or the liquid outside. So it goes from high to low. Okay. Student also measures the length. Assuming that the length has the same percentage change as the mass, calculate the final length of cylinder the concentrated solution. Right. Calculate the percentage. Right. So what are we? So what's the change in mass? So assuming the length has the same percent, calculate the final length. Okay. Right. So what we need to do is work out. We need to work out this percentage change first. Where are we? This one. Oh, this one. Yeah. So the original mass is that. So 2.1 minus 1.8 is. We're not interested in the minus. Yeah. We'll leave it there. Over the original, over 2.1. So over 2.1 divided by 2.1, and you get a number of 0.143. And then to turn that into a percentage, multiply by 100. So the percentage change is minus 14.3%. So now we need to decrease the length. What was the original length? 5 centimeters. Right, let's do it down here. Let's do it down here. Watch this. Right, so we've lost 14.3%. So look, if I do 100%, I'm going to use the multiplier method. Yeah, 100% minus 14.3% equals 70. Oh, right. Not 70. Sorry. 85.5 5.7%. I'm going to try doing all in one go. I'll need the calculator. Right, so it will be 5.0 times, as a percentage, that will be 0.857. Right, okay. What I'm going to do is I'm going to do it both ways just to, you know, it would help. It would help if I can do simple calculations. 14.3%. Right, okay. 82.7. My word. Excuse me, you have to excuse me. You have to, oh, what's going on? I don't know what's going on. Right. Let's forget that. Right. Let's undo that. Undo that. Right. Let's just stick to that. 5 times 0.857 equals, sometimes I make things too complicated. 4.28, whatever, equals 4.285 centimeters, which is 4.28, or yeah, 28. We can put 4.29, we can put 4.3. So anything in between there they can do. Right, that's fine. Right, the other way to do it is to work out 14.3% of 5. That equals minus 0.71. 0.71. So then we do 5 minus 0.71 equals 4.28ish. So it gives the same answer. So I've just taken this bit from the mark scheme, tried to be clever and do that in my head, and eventually got there. Right, that's fair enough. Right, let's have a look. Oh, we're on question number, right, okay, there you go. So now we're looking at food webs. So let's go through that again. That is the, no, I keep calling it primary producer because it makes its own food. These are the primary consumers, and these are the secondary consumers. Alright. Right. Which organism is the primary consumer? It's one of these. Zebra. Okay. Which of these has the least efficient energy transfer? Ooh. You lose 10%. I don't know. Which of these has the least energy transfer? Gazelle. Gazelle. Least energy transfer. Right, is that because it's running the fastest? Right. Right. Giraffe to cheetah. Stargrass. Okay, this is right. Let me just try to make it a bit smaller so I can see, because this is causing me a lot of headache. Right, let's try this then. So they're saying from giraffe to cheetah. Right, they're saying that's one of them. Then you've got star to baboon. Then you've got wild beast to wild dog. And then finally you've got zebra to lion. Where's zebra? Zebra. Okay, that. Right, okay. You always get energy transfers is dropping each time, but this one here, right, not all of it's going to be eaten. It's going to be wasted, excretion, and there'll be a lot of waste. You can't eat the roots, etc., etc. So which of these has the least efficient energy transfer? So it'll always be from primary to one of them. So they're more efficient when they grab hold of them. And that's what it is. It's stargrass to baboon. We'll have to live with that. Okay, let's go back. Let's go back. Take you back where you were. Right, okay, let's crack on. Which organism will be the least affected by a reduction of population of stargrass? Right. The giraffe. Baboon. 1, 2, 3. Okay. It will be the gazelle. Right, let me rub this out. Come on. Right, look at this carefully. Right, if you look, the gazelle has got two sources of food. It's got that and that. So if this dies off, the gazelle can still eat the acacia. So the one that's least affected is the gazelle. Right, okay. Again, this is now a standard answer. Why only a small proportion of energy in a trophic level is transferred to the next trophic level? Standard answer, yeah. So not all the organism is consumed. Some of the organism dies. So for example, if you're looking at the leaves, not all the leaves are eaten. First of all, some of them will drop down and won't get eaten, but they'll just decay. Some is not digested because there's some parts they're not digestible, so they'll come out as egestion. Some of the organism is released as waste, cell waste, so cell respiration waste. So for example, urea. Some of the plant is lost as heat or energy through movement, muscle movement, muscle contraction. So you can use any one of these. I'm just going off the mark scheme. 2, 4, 5. Okay, so you've got excretion, digestion, not all of it's consumed. There you go. Right, describe how a scientist could compare the population, right, of two ecosystems. So this is again the use of the word quadrat, not quadrant. That is a quarter of an axis grid. If you've got your x and y axes, that's your y axis, that's your x axis, this is a quadrant, it's another quadrant, another quadrant. It's not that, it's a quadrat. Right, so place a quadrat in a random location. Right, do you know what I'm going to do is, I've started off that badly, so what I'm going to do is do that, move that down. Let's be professional. Let's be professional. Right, let's start that here. Right. Split the field or ecosystem into a grid. Use a computer to generate random grid coordinates. Place the quadrant in the random location. Count the star grass. Would you count? Yeah, I suppose you could count it, because if you start digging it out, then I don't know. So count the star grass in each quadrat. Then what you do is you repeat a few times. Remove any anomalies. Average out the results, and then multiply up, right? And then you can compare. Done. This is a standard question that comes up a lot, really a lot. Wild dogs hunt a variety of prey species. They usually eat the weak, and kind of split how may benefit the species the dog hunts. Right. So the weakest prey is killed. So only strongest reproduce, passing on the healthy alleles to offspring. Offspring are healthy and survive. Come on, healthy and survive. When they survive, you also, do you know when you the weak prey does not pass on disease or pathogens. Okay, I think that's good. Right, Right, no, we'll stop that there. Right, we'll do the next one in the next video.